Thank you. Yes, it's not quite particle physics, but we're doing our best on Orphalus. So yesterday you heard Simon's talk on CHERI as an architecture and kind of the co-design we've been doing around it. And so thought we would take advantage of the fact that there are two of us to give a second talk and tell you a bit more about CHERI. I'm going to focus on software use cases and the co-design with architecture, trying to understand how the tensions that arise there. As has been pointed out, we might have a few co-authors. Of course, Simon is here, collaborator, largely working architecture and then down, and my role has been kind of more architecture and up. But after you do this for a few years, and we've been doing it for 7 years, things get a bit mixed up. And of course, Peter Neumann at SRI, long member of the computer security community, and many others. When you run a 7-year hardware software co-design project with 20 or 30 people, you do pick up people at all parts of the spectrum, from microarchitecture up through compiler design and so on. So what I'm going to do is tell you, just again, a little bit about the CHERI architecture. I'm going to tell you similar things to what Simon told you, but from a slightly different perspective, in particular with a software motivation. Talk to you a little bit about the methodology, and then think about what happens when we scale these ideas up to large software stacks. And Richard was very kind in describing our project. One of the things that we do kind of pride ourselves on is having taken evaluation much further than many investigations of computer architecture. We like to work with FPGA-based prototypes, but at the same time build complete operating system stacks. And we work with multi-million lines of code corpuses to try and investigate the effects of architectural change. I'm going to let you know that if you want to learn more about this, we do have a website which has technical reports, open source processor designs, software stacks, and so on. Right now, the sort of authoritative reference on our architectural approach is our architecture ISA document. We're now at version 6. We do about 1 a year. We'll do for version 7 pretty soon. But in light of Richard's comments, I thought I might mention that we also have a recent technical report on how CHERI interacts with Spectre. I think the result there was a bit surprising to us. We pitch our work as an architectural security approach. We rely on the microarchitecture doing what we think it should do. And as with memory management units, there's an expectation that you can build isolation, and lots of things are grounded in the concept of isolation. And so Spectre challenges that assumption. The surprising thing was not that we might be vulnerable to Spectre, but that in some situations we might not be vulnerable to Spectre. And as Richard pointed out, this relies on implementing it well in the microarchitecture. So we have a new set of requirements for implementing our instruction set architecture in terms of mapping down into superscalar behavior. And this report talks a bit about it. There are other aspects of Spectre where we are vulnerable, and we have modest extensions to our architecture, which we hope, after a bit of prototyping, we'll be able to show help mitigate other aspects of it. So on the hardware-software co-design thing, we have been doing it 7 years. We're approaching our 8th year. It's a joint research project between SRI in California, here at the University of Cambridge. And actually, recently, we've added on research to a new phase of the project, looking at the impact of CHERI on microcontrollers, heterogeneous compute, and so on. The focus has been architectural mitigation of vulnerabilities in C and C++ language trusted computing bases. So we believe high-level languages are a great idea. We think you should use them. We then rapidly point out you appear not to be using them, and also that your high-level language runtimes are often implemented in C and C++. And one neat property of that is that your language runtime can have surprising vulnerabilities. For example, Ruby has been demonstrated to have format string vulnerabilities, even though it doesn't support format strings. So that is our focus. We do this through a bunch of architectural features, tagged memory, and capabilities that Simon has told you about. But then what do we use it for? We are interested in mapping up into software protection properties. And there, protection is a heavily overloaded word. In this context, what we mean is the ability to constrain software to some of its intended uses, that we somehow carry forward a specification for behavior that isn't just the description of the program, but allows us to cause the program to fail or fault or be constrained if it acts outside of those goals. If we think about what a memory management unit is for, sort of conventional virtual memory, the goal is the same. The protection aspect of it is the thing that prevents you from accidentally or intentionally writing on memory you're not supposed to. So we'll come back to some of those concepts. Another thing that we do is we look at it from a sort of fine-grained memory protection perspective, sort of language-facing. We also do fine-grained compartmentalization. Fine-grained memory protection, we try to lift properties that may already exist in the language that the programmer might assume but might not be true. In compartmentalization, we restructure software more overtly around the principle of least privilege. Fine-grained pointer protection generally comes, and memory protection comes at a performance cost, hopefully low. Compartmentalization comes at an enormous performance improvement. The goal here is orders of magnitude improvement over current architectures, which is how you justify architectural change. And then I guess a last thrust, which is really important, is incremental adoptability. The fact that you can slide it in with your existing software stacks, assuming you're willing to ship some new hardware, and then maintain that over time. It's obviously an important aspect of transition. On the whole, we turn to the principle of least privilege. We use these capability-oriented designs, and we've now, through red teams, formal verification efforts, and so on, demonstrated significant mitigation of software vulnerabilities. Not all vulnerabilities, but some classes we do a pretty good job. We mentioned this is hardware-software co-design. It's actually hardware-software formal model co-design. We work across all, and we have a bunch of artifacts. We start off with an abstract protection model. This helps us think about what we want from protection in software. We then map this into specific architectures. For example, if we map it into MIPS, then we end up with a concrete ISA we can go off and implement and write software against. We build a formal model of the instruction set as we go. This is a methodology we picked up over the course of the project. It improves our productivity. It also allows us to use the tools of formal verification. We can do automatic test generation. We can prove properties of the instruction set. We can actually rerun proofs in continuous integration and convince ourselves we've not broken the properties as we extend the instruction set. And this is really important. If you were to transition this technology, you would want to know as you continue to adjust and extend the baseline instruction set that the properties are still true. Everyone's always adding new vector instructions and various things. You want to know as you extend your architecture, you don't break the essential security properties. So we work with formal models. They're also executable. We have QEMU, we have FPGA prototypes. We then build compilers and operating systems, and we run real-world applications. And we perform evaluation. We look at compatibility, security, performance, microarchitectural cost, and we do it over and over again as we refine the model and improve it. And we've done quite a lot of that. So let me briefly reintroduce you to the idea of perhaps the lack of architectural least privilege. So I'll remind you that in our architectures, we have a program counter of some sort. We have a set of registers. We have some memory. In a classical buffer overflow attack, which I realize at this point feels a bit gauche and stale, and yet we still suffer from them, there is some string buffer. There is some register with a length. There's a return address put by the compiler helpfully above the string buffer. The attacker injects, bypasses notional bounds checking if present because it's wrong, or maybe it's just not present, which is common. Overwrites the return address. Some data goes into a return address register, ends up in the program counter, and this gives the attacker something really powerful. It gives them arbitrary code execution. And lots of architectural and software mitigation techniques attack this, but we could reinterpret this problem in terms of a privilege problem. We could say, well, the language didn't want us to do all these things. It said nothing about return addresses. Why were we able to write outside the target buffer or inject a code pointer, execute data as code perhaps, or reuse existing code? So if we thought of this as a privilege problem, we could think about limiting those privileges. And ideally, we would allow the code to operate as we intended, and prevent some of these undesired effects from occurring. And this doesn't make the bug go away. Right? Instead, it says it's not exploitable. And the observation that motivates much of what we do is that current memory management units, the world's current memory protection technology of choice and architecture, is really not designed for this in any way. So just step through a couple of design goals. Architectural security, C and C++ trusted computing bases. What we want to do is provide efficient primitives for use by software in implementing privilege reduction at various levels of abstraction, and also then this principle of intentional use that Simon mentioned. So the idea here is that when we implement at architectural level the use of privilege today in memory management units, there seems to be this disconnect between the rights that we're given and the rights that we exercise. So if you think about a pointer is an integer. If we corrupt the integer, then we can still use it to access data. And in particular, the memory management unit will happily take any pointer you give us, any integer, and try and find some piece of memory that matches it. So it doesn't say use this specific piece of memory in a way that is strongly constrained. It says use a piece of memory addressed using this pointer. So in a design for intentional use, we would connect those two ideas more directly. We wouldn't allow confusion to arise when a pointer is corrupted. I'll come back to that idea. But this principle is all the way through our architecture everywhere we can put it. The only real exception to that is where we want to maximize compatibility, and we then have to try and figure out what right you meant to use. Something to do with a bit of caution. Another key insight is the deconflation of two quite distinct ideas, the notion of virtualization and the notion of protection. Memory management units combine these two ideas, and an important aspect of the CHERI design is that we're going to separate them because they have different performance overheads. Virtualization is provided by the memory management unit. Right? It's about the location of data. We take an integer, which is the address. We go find the information we need by looking in tables. Protection doesn't really require that. Protection is associated with indirection, and in the memory management unit we use it that way by saying, well, when we go find the memory, maybe we have some permissions. In CHERI, we're going to add some new protections onto some existing indirection, the pointers you already have floating around in your program, or maybe some new pointers you choose to add. So we can avoid table lookups, which is an integral aspect of the design. Once you have these capabilities, you can do some good stuff. We can build isolated compartments with efficient sharing. We can also do language-oriented memory protection. But a key design everywhere, and sometimes this comes out of yours, the classic capabilities system question, which is, what about revocation? We'll tell you, well, we've chosen to maximize the degree to which we're not looking in tables microarchitecturally, and therefore there's a trade-off around the ability to do certain kinds of other things. So it's a hybrid architecture. That means that we want to blend these ideas about capability systems with contemporary architectures. MIPS not particularly contemporary, but there are more contemporary RISC ISAs one could look at. We want to blend naturally with memory management units and programming languages and operating systems. We're going to use these capabilities to protect things within virtual address spaces. So we're going to use the two as complementary techniques. We're going to keep the MMU because it's quite useful, but we're going to use capabilities for other things, and sometimes we'll shift use from one to the other. And of course, there is this incremental software deployment path goal. So just to reiterate the point, architecture provides mechanism, software provides policy. So where does the policy come from in CHERI? Well, it comes from one of two places today. One of them is language-based properties. So we can turn to C and C++ and we can ask, well, what if these languages were memory-safe languages? What semantics would we want? How would this play out? We can look at types in the language, we can look at linkage information, we can look at runtime behavior and OS behavior. All of those give us origins of protection information that today is not enforced. There are also situations where we need new software abstractions. The architecture makes possible new software constructs in an efficient way. I mean, Turing complete computer, you can do whatever you want, but the goal is efficiency, because if it is inefficient, people are not going to do it. It's going to use too much energy, it's going to be too slow. So when we do need a new abstraction, we have to think about what it will be. When I say, oh, we're going to do things inside address spaces, it immediately tells us that our current operating system constructs, like processes, are not the ones we can use to describe software compartmentalization. So we might want new abstractions. So let's just pause for a moment, think about protection goals. So I said C language TCBs, so operating system kernels, language runtimes, web browsers. Often these things are all smashed together in our large trusted computing base. Is the web browser in the TCB? It certainly is. You visit your web banking in one tab, you go visit Gmail on the other tab, someone sends you an image with an attachment. How far will the exploit get? Well, with today's technologies, it gets all your Gmail access because it owns the tab, and the tab gives access to every message you have access to using Gmail. We would love to push it much further. They now own access to their own image. So we can do that kind of thing with CHERI. We're focused on granular, very spatial memory protection, pointer protection. This allows us to mitigate many common exploit techniques. CHERI provides foundations for temporal safety. It isn't the direct goal of CHERI to immediately solve this. Temporal safety is a very complicated problem. At least one of the things we would observe about it is people are often much more confused about the notion of allocated and free than you might think. It is not a straightforward concept in language runtimes, for example. And then we can also provide links to higher level languages. For example, we had a paper at ASPLOS a couple of years ago explaining how we could use CHERI on the JNI border to sandbox native code to impose Java memory safety on the native code interacting with Java. So we can do all kinds of interesting things. And then there's this in-process compartmentalization. For the remainder of the talk, I'm going to talk to you about the language-related properties, how we refine them, and then how we evaluate them. So we told you that CHERI provides protections for pointers. It actually provides a new basic architectural type, which can be used to implement pointers. It can also be used for other things, but let's focus on it as pointers. In the world of pointers, where do pointers come from? Well, from a user application perspective, your initial pointers are provided to you by the OS kernel. And in the world of dynamic linking and address space layout randomization, that is where you have to get your pointers from. Traditionally, you might find pointer values embedded in software itself, right? Statically linked programs or hard-coded addresses. ASLR made that all go away. We are not great fans of ASLR, but we appreciate what ASLR has done to software. It means that all pointers really do start in the kernel, and then they cascade down in this tree of inheritance. You get a pointer from the kernel, maybe to some bit of mapped memory, and then a heap allocator subdivides it. It does arithmetic, and now you derive more pointers from it. Same thing with stacks, same thing with code execution and runtime linking. They all cascade down. So what's interesting about this is the property of provenance validity that Simon mentioned yesterday, that pointers have valid provenance based on transforming existing pointers. So the language and the underlying code generation model actually aligns very well with the properties that we've been embedding in CHERI. So when we add integrity protection and provenance validity, what this tells us is that if we generate code against this, we now have guarantees that all pointers you can dereference have been transformed only in valid ways, that they have valid provenance back to some original point. And in particular, you can't just make up pointers anymore. You cannot inject them through a network data stream. So a bunch of exploit techniques just vanish by virtue of that. Our bounds mechanism allows us to try and limit how pointers can be used. We can use this using the heap allocator or the stack allocator and so on. This also helps us. What it really says is you can't access the wrong object using a valid pointer. Right? So somebody has to go through set those bounds. We'll come back to that in a moment. And then this monotonicity property. This says once you have a pointer, you can't escalate its privileges. It's not just that you can't refer to the wrong bit of memory, but actually you can't work your way back up this hierarchy. And then because code is also managed using pointers, we are concerned with control flow and so on. We're able to restrict the bounds and the permissions and the behavior generally of control flow pointers, which means you can't inject those either. Thinking about this for a moment, yesterday there was a question about signed pointers in ARM. So signed pointers in ARM help us on the right-hand side with the integrity of code pointers. They say nothing about the left-hand side. So data pointer injection remains entirely plausible when you have a signed code pointer mechanism. The permissions mechanism allows us to have quite strong invariance. For example, you can't have a pointer that is both writable and also executable. So let's just think slightly more about pointers today. So pointer today is an integer virtual address. It sometimes points into a memory allocation. Sometimes it points into the right memory allocation. Allocations, memory mappings. Right? We derive pointers from other pointers. We use arithmetic in our architecture. We dereference. We perform jumps and loads and stores. There's no integrity protection, at least not really in current architectures. This is coming to some extent. There are arithmetic errors. You end up pointing where you don't mean, often into somebody else's memory allocation. Pointers can be valid and just be used for the wrong thing in the wrong way. Right? And the insight here is that as an attacker, pointers are really a powerful tool for us. So if we can use CHERI to help reinforce pointers, maybe we can help mitigate some of these vulnerabilities. So what does our CHERI capability look like? Well, we start with a virtual address. We extend them with this tag in memory that's going to provide strong architectural integrity and also allow us to enforce our provenance validity property. If we have an untagged capability, we'll throw an exception. If a capability is overwritten in memory, the tag will be transparently cleared, atomically cleared, and now it becomes non-dereferenceable. We add some bounds, a lower bound and upper bound. We add some permissions. This is starting to get pretty big. And then we also add some additional features to support compartmentalization that I won't focus on at this point. So from a protection model perspective, this is 256 bits. From an architectural perspective, this is actually 128 bits. And I'll explain the details. What we do is we compress the bounds, which have a lot of redundancy bitwise with respect to your pointer, like the lower bound and the upper bound. The pointer's usually in between, and they share the left-hand side of those bits. And we can actually use that for compression. So we use a floating point mechanism. This causes the bounds to have stronger alignment for larger memory allocations. This is something memory allocators deal with already. But the important thing is that when we fit the stuff into 128 bits, we maintain all the current security properties, especially the monotonicity property. We can invest those bits in different ways for different kinds of things. And we also maintain strong C language support, a topic I will say more about in just a moment. When you move to 128 bits, pointer density goes up in memory, and so we expend a little bit more physical memory. We go from half a percent to just below 1% of physical memory going into these tags, which is below the sort of roughly 3 to 5% memory overhead many companies think about when they talk about the effectiveness versus the cost of mitigation techniques. And we have all this running in FPGA with a complete software stack. So the architecture has evolved. We really started off prototyping the architecture, then moving into C language behaviors, compartmentalization models. And the last few years has been efficiency and transitionability. So what are the implications for software? Well, we told you the architecture provides some properties. For example, provenance validity. In order to say our software will work with this model, we have to know that pointers do come from valid places. Right? And this is, as I said, increasingly true thanks to ASLR. So that's a somewhat believable claim. Integrity, how do they move around the system? Is their integrity maintained? For example, do people encrypt and then decrypt pointers? Because our tagging mechanism will not approve of that. Right? Bounds and permissions. It's not just, do things follow their bounds, which should be pointed out they're not very good at doing sometimes, but also, where do you set the bounds? Who knows what the bounds should be? Because the architecture doesn't know that. That's software policy. And then monotonicity. We've said, there's monotonicity on pointers. Can real software play by those rules? Is software monotonic in its memory allocation and memory access? And then on the compartmentalization front, which I will talk less about, the same questions arise, right? Can you construct isolation and controlled communication? do you end up with better semantics from a software authorship and scalability perspective? So we've really worked with two kinds of code to date. So the first is what we call this hybrid capability user space code. So this is designed to work with the current MIPS API. It was our early investigation. We have manual annotations that tell us this thing should be a capability, that type should be a capability, oh, maybe this one is an integer pointer. But importantly, a lot of the runtime around our code was not using capabilities. It was still using integer pointers. For example, pointers you pass into the kernel. So this is important. If you have a user space memory model that your kernel does not observe, and you want to break the memory model as an attacker, you just make recourse to the kernel. You say, well, user space would never overrun this buffer, but let's just ask the kernel to load data off the end of the buffer using our I/O routines. So really, you want the kernel to be aware of and fully enforce the memory model. And we can build a lot on top of that if we have it. The last few years, we've been working with pure capability code. This is code where all pointers are just implicitly capability. No annotation is required. And it's not just the explicit pointers, it's the return addresses and the vtable pointers and all the other implied virtual addresses you dereference inside of program execution. So automatic use of capabilities and absolutely everything we possibly can. It's the extreme point in the space, so it allows us to evaluate compatibility and performance and so on. We're now actually deploying these ideas inside OS kernels as well. So to do that, what do we have to do? We need a pure capability compiler, we need an operating system and a process environment. We can run this code. We need to adapt all the user space applications that we can possibly find. We then need to measure compatibility, performance, and protection. We need to revise it when we've discovered that actually it didn't do what we wanted. And we need to do it over and over and over again. Good stuff. So what is this CheriABI I mentioned at the start of the talk? Well, it is a version of the FreeBSD operating system that has all of these properties. We adapted the system libraries, the C startup code and runtime, base low-level libraries, every system daemon and tool in the base system, which is stuff like OpenSSH and OpenSSL and so on, a complete set of applications, programs like Nginx and Postgres. We're in the throes of bringing out WebKit as our C++ support gets more mature. And it forced us to answer a lot of questions. Right? Where do the pointers come from? Who minimizes the pointers? All over the place. The pointers start out in these kernel-provided routes, and architecturally we require that. User space cannot make up a pointer. Our compiler generates code that refines capabilities. It reduces the bounds, for example, or modifies the permissions based on types or in the stack allocator. The runtime linker goes through and sets up bounds on code. Right now we tend to use the shared object as the bounds, but actually we have a prototype that does per function bounds. This gives us really strong control flow robustness. But somebody has to do these refinements of rights, and this is, as I said, a source of policy. And sometimes you get really annoying trade-offs. For example, we said we want to minimize privilege, we want to have monotonicity, and we also want to use current APIs. That is a great idea until you get to realloc. So what does realloc do? Realloc says, let me give you a pointer, and then return a pointer, which could be the same pointer virtual address or a different virtual address that has access to more space. So that is a non-monotonic operation. So part of the idea of realloc is it returns a pointer that if it is the same pointer, the data is already there waiting for you, and it's actually managed to say, oh, there's a bit more space, my buddy allocator or whatever off the end. I'll just expand the bounds on it. So is that the same pointer or not? It's a different pointer, and it's a pointer which has different bounds. So sometimes we find we have to go back and rederive pointers because we can't directly express that non-monotonicity. We have to make an overt call into privilege in order to do that. mmap is very similar. Mmap happily returns a pointer with certain rights. Oh, it's readable and writable. And later you do mprotect and say, make it executable, but not writable. Well, that is a non-monotonic transformation because mprotect does not return a new pointer. So there's an argument we should either end up with more rights than we want on the pointers, or a new mprotect API that returns a new pointer. Right? And there's a trade-off, protection versus software adaptation. And most of the changes we find like this are in the memory allocator. System people own this thing. They're willing to change it and adapt it, language runtimes. But if you touch APIs that are more widely used by realloc, you have to be really careful. So when you do this, you get what I would think of as the grand tour of low-level OS behavior. There are bits of the OS I didn't know existed, and now we are intimately familiar with its downsides. So we started off with what we think of as our hybrid ABI kernel. This allowed us to run capability code in user space. It meant the virtual memory subsystem supported tagging and context switching and signals and all that good stuff. But then you hit user space, right? And user space memory copy has to preserve tags. If you do integer memory copies, tags all disappear, for example. But it's not just memory copy. Turns out sort is also memory copy because people sort pointers. I didn't know that. Anyway, so that also has to be tag preserving. You have to set your bounds in your memory allocator. All kinds of interesting things arise. How do debuggers work? We then do CheriABI, and we say, okay, well, the kernel doesn't change very much. You have to have a system call interface that carries capabilities back and forth and uses them. but the guts of the kernel could remain hybrid code. But in user space, we have to run all over the place. And it's not just argv that goes into your user process. There are all these elf auxiliary arguments that set up the runtime linker. All of those things become capabilities and requires us to work through, review, and improve a lot of code. We'll come back to integers and pointers in just a moment. But it also involves things like the runtime linker and new relocation types. So the normal thing people say when they see a presentation like Simon's yesterday is, so you made integers and pointers different from each other as architectural types. What about pointers and integers? Let me give you a quick list of interesting things. So C programmers, you're probably a C programmer, know that pointers and integers are completely interchangeable, and you can do any arithmetic you want on it, and you probably do. You exclusive OR them by things, you add them up, you do all kinds of stuff. Turns out this breaks a lot of contemporary compiler optimization, so there is a gentle pressure coming from another community to do this, just a little bit less. But for us, these pointers are actually something much stronger, right? They have all these architectural protections. So they carry around additional metadata, like tags, and we have to make sure that when we want to preserve it, we do, but when we don't, we don't. For example, when we memcopy a data structure with pointers in user space, we'd like them to be pointers when we're done. But when we send a packet over UDP or via TCP on the loopback interface, we'd like the tags not to get to the destination because we're not sending pointers, we're sending data. Right? Likewise, we have these additional in-band things. We are carrying around larger pointers that actually have stronger alignment requirements. And then we have these auditor properties like provenance validity and monotonicity. Right? We need to know that software can work with that. So stronger alignment. Well, most software, by the way, just fine with stronger alignment. It is already portable between 32-bit and 64-bit code, and occasionally you discover those numbers are hard-coded. Not really a problem, but then you discover people like to stick pointers into hash tables designed to store in files using Berkeley DB. Okay, so I guess you can't do that anymore. We modified our memcopies, as I mentioned. That's not so bad, and pointer arithmetic almost always just works in the compilation model that we're using. And people can do the usual tricks, like twiddling the low bits, very popular thing to do in language runtimes and kernels and locks. That pretty much just works. But then people cast back and forth pointer, integer, pointer. So if you cast through a long in our environment, a long is the largest integer type. So the provenance is discarded because you can't carry a tagged capability through it. Right? So that means you might have to change your code to use int pointed t, which is something that is large enough to hold a capability. Which is great because it does preserve the provenance and metadata. But then actually is that the semantic you wanted? So we usually find these confusions in low-level pieces of code like malloc, to be honest, and runtime linkers. We don't tend to find very much of this in high-level applications, at least until you find a program like Postgres, which is run on every architecture and every Unix system ever, and therefore carries a complete copy of the system library just in case yours doesn't work. And then it uses it even if yours does work. So you discover some applications need changes. Last comments on pointers. So there are some APIs that are what I would call pointer ambiguous. People aren't sure if they want a pointer or not. iocta was the classic Unix system call that accepts something that might be a pointer. Only they use long because everyone knows that long is the size of a pointer. So we know that long is not the size of the pointer, and we discover we have to change these things or it really doesn't work. So it does perturb aspects of the system call API. And there are other places where contemporary code will use int pointer t, but long is just the historic thing. Another cute trick is something called NaN boxing. So this takes advantage of the fact that there is a NaN space in floating point numbers, and you can use a single long to hold either a pointer or a floating point number, and you can tell the difference by looking at these NaN bits. This is cute, but it causes a problem for our bounds compression because it is almost always work in the upper left-hand bits, and if you start twiddling those bits, you push the pointer a long way out of bounds if you kind of think about what the virtual address is, and you could end up with something that is non-dereferenceable. The good news is we now provide tags, so you can reliably identify pointers, but it actually does require code change. And this is a very popular technique in JavaScript runtimes, for example. I mentioned monotonicity. Well, there are pieces of code that need to broaden bounds. This is almost always something that thinks it is a memory allocator. So when we free, we start off with a narrowed pointer, and we have to find our way back to the container because people like to store the metadata just outside of the bounds. But you can't access that metadata, which is great for preventing exploits, but really terrible if you need to access the metadata. So we discover you end up with these privileged structures. Well, the cute question is pointer equality. Suppose you have two pointers, have the same virtual address, but they have different bounds. Should the language think that they are equal to each other? Well, I mean, the natural thing to do is to assume that the virtual addresses are equal. They should be equal, and code works better on the whole if you do that, unless it uses realloc, where you return a pointer, and if you do a virtual address comparison, you're not actually checking to see the bounds have changed. Therefore, you use the old pointer with the old bounds. It all falls apart. So there really are some tensions around this notion of pointer equality, and we've recently ran into some in Qt WebKit, which are causing us some frustration. There are some also high-level requirements. We were able to express garbage collection for C because we can reliably walk through memory and find all the pointers. They're tagged, so we can do accurate garbage collection. But we can't do it if you frequently push virtual addresses through integers and then push them back into pointers. In fact, we will generally prevent you from doing that. But there is a tension about the extent to which you're willing to mask that behavior. There are lots of choices in how you use our primitives in the language and in code generation. We find that there tends to be garbage collectible C and then not particularly garbage collectible C. And the degree to which we provide compatibility between them depends a bit on the goals. And then there are some really obscure things, which I'll just mention for amusement value. Our varargs implementation has much more type safety and memory safety, but it turns out that means it has a different ABI. And a lot of old code doesn't distinguish between the ABIs. It doesn't have function prototypes, which tell us when we generate caller-side code and callee-side code that they should match. So if we change the ABI of a varargs code, when we use a function pointer that isn't varargs, we end up with an ABI incompatibility. It is definitely a bug, but how many bugs do you want to find of that sort? It turns out less, or more rather, is all this kind of bug. Huge files without arguments and function prototype, very 1980s. Then one more cute thing people do. People like to pass pointers between processes using Unix domain sockets, it turns out. You might think this is a terrible idea, but it turns out if you fork the two processes from each other, you actually know they have the same layout. And people actually do this for a reason that is slightly awkward for us to talk about, which is they've been trying to compartmentalize software. So they will fork a second process, sandbox it, and then pass a function pointer across the Unix domain socket and say, just go run this code. I'm sorry, we don't allow that. But it's a choice in our OS design. We could allow that, right? We could carry tag data through Unix domain sockets. Just a couple of thoughts on evaluation. So we have done a lot of evaluation on this. So the first thing we do is we build our compiler, and then we build a complete operating system. 2 years goes past. Right. So one of our goals was little or no change to current software. And I think to a large extent we've succeeded in doing that. We still go back and forth a bit. We're playing with different adaptations of C and integer pointer behaviors and so on a pretty regular basis. We have new compiler warnings, help us find potentially risky code. Just at a high level, FreeBSC's base system has 130 libraries from zlib to crypto code and so on. We had to change 28 of these. Most of these were low-level system components, like parts of the runtime linker, or just really ancient C code. Overall, there are 20,000 source code files in the FreeBSC base system for user space, and we had to change roughly 200. And the categories of change pretty well understood. We're increasingly able to find places where we do have to change using compiler warnings. What kinds of problems we run into? Well, the ones I've mentioned, possibly poor alignment or the decision to use function ABIs poorly and so on. We also want to know this software works. It is not sufficient to compile the software. So we use the FreeBSC test suite to do this. The FreeBSC test suite probably doesn't have quite the coverage that we would like. Today, we are actually quite successful with this. We run into roughly 2 problems. When I generated this chart, we're not yet routinely using runtime linking. And there are certain tests that really rely on runtime linking relating to pluggable authentication modules and so on. Those are now largely believed to be resolved. We have some other failure cases that we're currently working through that are probably cases of C language use which we are not able to find using warnings. I suspect we'll educate ourselves a bit more. But the upshot is actually quite interesting. It's the vast majority of C code does just work. For example, we make no changes to OpenSSH or OpenSSL in order to compile them and run them, which means we get spatially memory-safe OpenSSH and OpenSSL essentially for free from a programmer perspective once we do this. It's also important to think about the memory protection impact. So this is quite hard to do. I mean, proving it's more secure than before, we know is a challenging issue. One thing we can do is go back and look at past vulnerabilities. And because the project has been running for a while, we can also look at vulnerabilities that arose after we started designing the protection model. So for example, although return-oriented programming was not a popular thing when we started our work, it is now quite a popular thing, and it is simply not expressible in our architecture. You cannot inject a pointer sent over a TCP socket. Buffer overflows, of course, were in our threat model, but there have been a bunch of very influential ones since we started. There are some other more interesting ones. So stack clash is a neat vulnerability in which a pointer intended to use for one memory mapping is used for another, typically bopping off the bottom of one stack onto another thread stack that happens to be adjacent to it in memory. So our bounds prevent that, but so does our notion of provenance, the idea that you can't use a pointer to one object in another way or for the wrong thing, that pointers have to come from the right place, and in terms of our intentionality, they have to be used for the right thing. There are test suites. There's a buffer overflow diagnostic test suite. This is primarily used for static analysis tools. We do fine. We actually do very slightly better than address sanitizer, which comes at something like 6 times the executable cost of what we do. A key evaluation concern is what happens if your adversary knows about your protection mechanism. And this, of course, is where most control flow integrity-based techniques fall down. We make it harder for you to do something, and then somebody finds another way to do it. So we have to think about a CHERI-aware adversary. This is actually quite hard, and we've thought a bit about it. When I say, oh, you can't express return-oriented programming because you can't inject a pointer, well, a reasonable adversary would say, well, yes, fine, but I will reuse the pointers you already have in your address space. So now it is a question of spatial memory protection or temporal memory protection. How many pointers are exposed that could be used in this way? Can you find code generation that allows you to do that? Are there the ability to move around within functions if the bounds are set to the bounds of the function? There's also more interesting recent stuff, such as spectrum meltdown, which happily Richard has used his minutes to describe, or somebody's minutes to describe. So when we want to understand how the CHERI-aware adversary thinks, what we really want to do is understand how CHERI is impacting software. A really neat thing about CHERI, right, an intentional aspect of the design, is the fact that pointers are visible in the architecture, and you can't dereference something unless it has been visible to the architecture. So one thing we can do is extract traces of execution in QMU or an FPGA, and we can then construct pointer provenance graphs. These allow us to track the flow of all pointers through the address space, what is reachable through them, the contents of memory at various points. So in this graph, we just have a plot of the address space where we're looking at where bounds are set at various points in execution, such as the initialization of global variables or initial access to setting up the heap, stack use as the program executes. So we can actually go back through an execution and ask, what pointers would have been exposed, right? Should we have invested more resource in clearing memory when we freed memory, or whatever it is that we might want to do? So we can do things like look at allocations, look at the propagation of capabilities, and actually reconstruct very high-level software behavior out of this pointer behavior, such as sandbox behaviors. Another kind of thing we can do is the quantitative measurement of rights reduction. So when we look at bound setting at scale, we can ask, how small are the bounds getting? Because this is some notion of approximation of least privilege. And we can look across a bunch of behaviors. So in this plot on the left-hand side, we have a CDF with a bunch of different compiled versions using different policies for bound setting. For example, are you using OpenSSL's own malloc, which doesn't set bounds, or our malloc that does? So the goal here, this is down here, is the width of the bounds in exponential notation. So when you start out, all your bounds are set to the entire address space. Right? But as we modify the program, increasing numbers of pointers have extremely narrow bounds. So this doesn't tell us what is not exploitable, but it does tell us that we are pushing in the direction of least privilege, which at least intuitively helps us think it is a good idea. So just to wrap up a little bit. So I've told you new architectural primitives really require software adaptation, a rich evaluation model. They also require is a co-design methodology, because simply saying, here is my new architecture, let's see how it works on a small scale, is completely inadequate for deciding if software actually works. So one very interesting thing that came out of our work in bounds protection is a discovery that almost all existing bounds protection literature didn't work. So one of the assumptions made in a lot of that literature is that pointers are always in bounds. Now we enforce that they only be dereferenced when they're in bounds, but we don't require that they be in bounds when they're not dereferenced. And if you look at low-level software like zlib or tcpdump, a number of low-level system libraries, they will frequently take a pointer out of bounds by a small or maybe a large amount. We've seen approaching 100K in one instance. If your bounds checking mechanism doesn't allow that to be expressed, the software will not work. So that tells us that in the evaluation of the existing bounds checking systems, they never ran zlib. If they didn't run zlib, we are really in trouble. So we have a lot of different usage patterns for our primitives, and so a lot of our work has been trying to figure out what the right usage patterns are. So the pure capability code generation model is a very strong model. It comes at some amount of disruption. It's very different from our compartmentalization usage model. And we're really still working through, what would we advise people to do if they were deploying this architecture? And it is incrementally deployable. They can do this for one process, but not another. Right? They tend to not be able to combine them in the same process very easily because pointer size differences make that awkward, although there are things you can do. We believe the best validation approach for this is really through hardware-software prototypes, the ability to look at the microarchitectural impact, look at memory behaviors. I mean, one of the things that we didn't understand before we began more collaboration with companies like ARM is the extent to which it wasn't performance on the core that mattered, but actually cache misses that mattered out of the low-level cache. For them in mobile devices, additional DRAM loads are the single greatest source of additional uncontrollable energy use. So by increasing the size of pointers, what they really want to know is how many new DRAM accesses are they. They don't want to know how fast did the software run. I mean, they care about that, but causing the battery to drain 20% faster is not going to be okay. So a lot of our follow-on work, as Simon was describing, in tag behavior is really how do you get those additional DRAM accesses down, which we have not found any use of that methodology in current architectural literature when talking about security. So interesting things arise. Our CheriABI model that I've described to you is really about the ubiquitous use of these features and how do you compose with the MMU-based model. And I think we've shown that there are pretty good trade-offs to be found there. Right? They come at some compatibility costs, and although I haven't talked about it, they do come at some performance costs. It tends to be very reasonable. And overall, what we're trying to do philosophically is expose more of program structure to the architecture explicitly so that we can have the architecture self-check those aspects, whether the programmer asked us to or not. So I will point you at our website, and I'm probably running long, but in as much as there is time, I'm happy to take any questions. Thank you very much.
We are a bit over time, but let's have just one question, maybe, if somebody has one. Yeah.
So it seems to me some of the problems you're addressing with CHERI could equally be tackled with the same systems level programming language, let's say Rust. So how would you compare, say, the expressiveness performance impact?
I think this is a good question. I mean, our encouragement generally is you should write your software in safe managed languages, and I think I'm very supportive of the Rust effort. One question that arises very quickly in Rust, I mean, it's some very nice properties, especially temporal safety properties. The linearity property, for example, is really interesting. One of the goals of Rust, though, is to interact with existing system code through an FFI. The moment you enter that FFI, all guarantees are lost in Rust. Right? It's privileged code, and we just have to trust it. Although we haven't implemented this, one thing that would be quite interesting to try is to say, well, let's use capabilities around the native code so that when we carry references in and out of Rust, we have guarantees that Rust can now depend on. So this means that as you expand your pool of Rust code, you are not forced to shrink the native code unless you need to for performance reasons or you're able to rewrite it. Maybe we can get stronger guarantees. So I think definitely not discourage the use of Rust, but I think of it as a complementary technique. There is an interesting question. Suppose the whole world is managed languages. Why would you use a technique like ours? Well, there are some things that we provide architecturally that are very powerful to a language runtime. So, for example, the ability to know atomically that pointers have not become corrupted in the presence of concurrency, high-performance bounds checking, and so on. Those are all things that could be interesting targets for just-in-time compilers or compilation. We've not really pushed in that direction, not what we designed it for. We do know that talking to JIT authors and JVM authors, they have a huge problem with the correctness of the JIT, generating code that is not safe, where actually using CHERI as a JIT target might be very helpful because they would now get stronger guarantees. And generally speaking, that community would benefit from the techniques. The other thing is that some of the dynamic checking done in languages like Java and to some extent Rust depend on continuous checking. So you have a loop where you're walking down an array and you walk off the end of the array. That is supposed to be reported immediately and caught by the language. And if you look at the JIT generated code for that, or the compiled code, you have a lot of cost in it. Right? And we can actually take that cost out by using the primitive we have. You don't have to use CHERI to represent all pointers. You could just instantiate a capability the moment you begin to perform operations on a piece of memory with bounds and use it for bounds checking instead. So you could, in principle, use it to accelerate those languages as well, though, as I said, it's not something we've really tried or evaluated.
Thank you. Let's thank you.